Okay, guys, day 4, water retention. So now we've learned what the different types of soil are, what some soil textures and properties are, but we're going to focus specifically on how that soil retains water. So there's a little rules of thumb here to help you remember which soil is the best at it and which soil is not very good at it. But first, we got to define it. So what is water retention? Retention is the ability to hold. So water retention is the ability to hold water within a soil. So you retain it, your retention, you're holding that water within soil. So 3 main types of soil we're going to talk about is sand, silt, and clay. So if you look at the funny little pictures here, you see a lot of water going into sand and a lot of water coming out of sand. So is that good retention or bad retention? Does it hold water or doesn't it hold water? Let's look at silt. A lot of water going in. So we have 1, 2, 3, 4, 5 water droplets going in. We only have 3 come out. Clay, 1, 2, 3, 4, 5 water droplets going in, and then 2 tiny little droplets coming out. So which one was the best at holding water and not letting it go? Which had the best water retention? Think about it for a second. Pause the video and think about it for a second. Okay, so if you truly didn't cheat and you thought about it, hopefully you saw that clay holds on to the most water. There was the least amount of water coming out of it. Silt was in the middle. A little bit of water came out, but still there was some retained, and sand didn't retain any water. 5 droplets went in, 5 droplets came out. No water was retained at all. So now this graph looks intimidating. I don't want it to let you intimidate you. We're going to go over a few and we're going to practice some graphs, but this is not scary. So if you've convinced yourself it's scary, pause, do 5 jumping jacks, and then open it back up again. All right, hope you like that little workout. Now let's think about this with confidence. We have the percent of water over here on this side of the graph. You see that as it goes up. So 0%, 20%, 40%, 60%, 80%, 100% water. Over here, we have particle size of the soil. So we've learned previously that sand is the largest particle and clay is the smallest particle. So when the dot is right there, so let's put an imaginary circle right there. That tells me that at the particle size of 0.001, which we know is clay, really, really small, it retains about 7% of water. Is that retaining a lot of water? Absolutely not. That's retaining, percent going through. I said that backwards. Percent going through, now that I've confused everyone. So 7% is released. So how much is being retained? What's 100 minus 7? Hopefully you got that, right? I'm not going to give you the answer. You have to think about it. 100 minus 7. Now, that's how much is retained or held in. So that's a lot. And as the particle sizes get bigger, the percent of water being retained is not that much now. Look at sand. 10, so size of 10 millimeters. That's a big particle. Look how much is allowed through. 100%. 100% is allowed through. So what's 100 minus 100? Hopefully that's a much easier one. That's how much is retained. Not a lot. So we're going to practice these graphs. So don't freak out. You're not allowed to freak out. All right, so permeability. There's another fancy science word. What does permeability mean? It means how good is a soil at retaining water? That's permeability, the ability of water to move through soil. So in more specific terms, the ability of water to move through the holes in soil. So if you're super permeable, that means you got lots of holes, and that water is going to go whoop right through you. If you're not permeable, you don't got a lot of holes, and there's not going to be a lot of movement. There's not going to be a lot of water that travels through. So if you look, permeability, I have these awesome pictures for you to look at. Look at this one with sand. Again, we have 1, 2, 3, 4, 5 water droplets going in. We have 1, 2, 3, 4, 5 water droplets coming out. And it's at a rapid rate. So sand has a high permeability, lots of holes for water to travel through. Let's look at sandy loam or silt. We get 1, 2, 3, 4, 5 going in. We have about 3 coming out with a moderate speed. So that takes longer for the water to go through those holes because there's less holes. It's less permeable. And then we look at clay, teeny tiny little clay. Crazy packed together, super compact, no holes, no spaces. So that permeability is slow. It's super slow. It takes forever for that water to travel through, if it even travels through at all. All right, other science term, porosity. Porosity is just the definition for the holes I was talking about in the slide before. If you have a high porosity, you have large spaces. If you have a low porosity, you have small spaces. So, formal definition, the amount of spaces in the soil for air or water to travel or to be stored in. The higher the porosity, the more space for water and air to travel through. Thus, it has a higher permeability and less water retention. So the lower the porosity, the less space for water and air to travel through, which means it's low permeability, which means it has high water retention. Don't worry, we're going to make a chart showing all of this. And then, so again, higher porosity equals less water retention. Lower porosity means more water retention. Again, showing porosity and permeability and the definition of both. So porosity is the definition, amount of soil pore spaces. So look at that diagram there. Look how much space is in between the soil particles. That's high porosity. Permeability's definition is the ability of water to move through those spaces. So if we have lots of spaces, we have high porosity, we have high permeability. If we have low porosity or small spaces, we have low permeability. That's a harder ability for those water or particles or air to travel through those spaces. Is it good to retain water? What needs water? What in the soil grows in that soil that needs water? We've already learned about this a lot. We need water in that soil for our plants to grow. Do we care if our plants grow? Hopefully that answer is a yes. Maybe you don't care if that cactus grows in that desert. But if all the cacti die and that ecosystem disappears, trust me, you're going to feel it later. And we'll talk about that later too. So how do plants grow in soil that does not retain water? So let's talk about a desert. It's super hot in the desert. It's super dry in a desert. And the soil is sand. It doesn't retain water. Water goes whoop straight through it. So what can plants do to survive in that type of water retaining, non-water retaining soil? Well, we know already that cacti store their water in their what? Think about it. Their stems, right? So they store water. It's pretty cool that that plant can hold on to water and they protect it with those scary thorns. But they also have a cool root system. The roots are shallow. They only absorb water just a ½ inch or so below the surface. So the moment it rains, those roots are working hard to absorb everything that's on the surface. Because that water, once it hits the surface, it's going to drain quickly. It's going to go through that soil super quickly. So instead of the roots growing deep, they grow wide and they grow shallow. So they take up a lot of surface area, but don't go very deep because it'd be pointless for them to go deep. They're chasing just the water droplets at that point. But they absorb it as it hits the surface. That's their best chance of absorbing it. And don't forget, they also close their stomata during the day, so we don't have any transpiration. All right, so again, just showing you more images that you can use and look at to study and go through the practice. All right, seriously, go fix your pretest right now. Right now. Do not do anything else until you fix your pretest. Fix the answers. This is mom voice. Fix the answers. And then go on to the graph practice and making the chart. But not until you're done fixing your pretest. Okay, good job, guys.